right? I thought there'd be data. Is anyone out there?
Welcome back. A new homework just went up, and I didn't get the module up. I'll do that after class because that's what I would have been doing the last hour instead of running around the neighborhood looking for bugs. But there is a new homework posted, and I just wanted to let you know that one of them, actually two of them, I can't remember the numbers, they look super long, but they're not. There's an explanation behind them that's super long, but the actual problems are not super long. So don't be scared off by those. Yeah, so we are in the final fourth tool for important tools for mathematical statistics. Well, I am gonna share my screen. Okay, so we are in important tool number 4. And so following the notation, this is 4 in a circle in a box. And this is about moment generating functions, which I just barely got to define last time. And if you see MGFs, well, that's going to be moment generating functions. So if you have a random variable x, it could be discrete or continuous. The moment generating function is defined and denoted as usually an m for moment generating function, a sub x if it's necessary, like we've seen with our PDFs, if we have multiple random variables and it's confusing. And then it gets an argument that I was saying last time is usually a t or an s or a u, but whatever, just a real number. And it is defined to be the expected value of e to the tx. So I have 3 parts here, A, B, and C. And B is going to be about moments and what are moments and why does this generate moments. But A is just going to be computing a moment generating function. So I know you don't realize why you care about them at this point, but let's just compute one and then I'll try to convince you that you care. So I'm going to compute the moment generating function for the Poisson distribution with parameter lambda. So this is a discrete one. And so I'm just going to write it out. The moment generating function notation, m sub x of t, is the expected value of e to the t capital X. And because this is a discrete distribution, we get a sum over all x of e to the t little x times the probability that x equals little x. If it were continuous, we'd get an integral. And for our particular distribution, it takes values from 0 to infinity. So I get, not x, I get e to the tx times the Poisson PDF or PMF, which is e to the minus lambda, lambda to the x over x factorial. So in this class, you almost always, I'm going to make up a statistic, 97% of the problems, you do not actually have to do a sum or an integral, but you can get away with integrating without integrating or summing without summing. Let me rewrite this as another kind of Poisson thing. So I'm going to combine the e to the tx. So if you raise something to a power and then to another power, you get to multiply the exponents. So that e to the tx right there is e to the t raised to the x. So I'm going to combine it with the lambda. So I have lambda e to the t raised to the x over x factorial. And we can treat this like a new Poisson distribution, but in place of what is usually lambda, I now have this whole lambda e to the t. So going all the way over to the right here, this e to the minus lambda needs to be e to the minus lambda e to the t. So I'm going to just like put in things and take out things. I'm going to write this as this. I'm going to pull out the e to the minus lambda, and I'll leave a little space. I'm going to write in here what I want to see, which is e to the minus lambda e to the t, and then lambda e to the t to the x over x factorial. And in order to make that equal to the previous line, I need in front to put in an e to the positive lambda e to the t. Does that make sense? So for the sum, it's over x. So the t is like constant in the sum. So I'm treating it as a constant. So now this is the PDF for a Poisson with parameter lambda e to the t. And summed over all of these values, we get a 1. And so the final answer here is going to be e to the, how do I want to write this? To the e to the t times, oops, sorry, no, I want to pull out the lambda, sorry about that. To the lambda times e to the t minus 1, which we might write because exponents on exponents on exponents gets a little tedious. We might write as exp of lambda e to the t minus 1. And this sum converged no matter what t we used in here, because the Poisson lambda parameter needs to be non-negative. And for us, the t comes in up in the exponent of the e, and that's always non-negative. Like e to a negative would be 1 over e to a positive value. So there's no restriction on what t's will make this a proper Poisson distribution and make the sum converge. But a lot of the moment generating functions do have some restriction. When you're doing the integral or sum, you might need t in a certain range. So I wanted to have the distribution table ready to pull up, but I was running around looking for bugs. But if you look at your table of distributions, you don't have to right now, and you go to the moment generating function column, you'll see a lot of moment generating functions, and on some of them you'll see restrictions, like this holds for t less than lambda, or this holds for t in here. And so that just comes from the fact that a sum or integral wouldn't have converged. Okay, so why do we care? We care because moment generating functions, guess what? They generate moments. And what is a moment? And I'll tell you right now that I actually don't care about this. The value for me in moment generating functions is not in computing moments, it's in part C. So let's say we have a distribution for a random variable x. The moments for the distribution are the expected value of x, the expected value of x squared, the expected value of x cubed, on up. So the expected value of x to the k for k greater than or equal to 1 and an integer. This is how we're going to define moments, but if you need to make the distinction, these are called non-central moments. So I might like parenthetically stick in here. I mean, I don't want it there, otherwise I'd erase it and fix it. But these are called non-central moments, and we won't be needing central moments, but this first moment or expectation we denote by a mu. And just for the record, so you've heard of them, central moments look like the moments centered around the mean. So the expected value of x minus mu, which is just 0, so that's not interesting. But the expected value of x minus mu squared, which is the variance, so that's kind of interesting. The expected value of x minus mu cubed, which may or may not be interesting. So I'm going to, and it's very common, I'm going to call these moments, but technically they are non-central moments. They haven't been centered around the mean, and central moments mean something else. So apparently the moment generating function can generate moments. So check this out. The moment generating function for a random variable x is the expected value of e to the tx. And I am going to take the derivative with respect to t. So that is the derivative with respect to t of this expected value. And I'm going to move the derivative inside the expectation. We'll eventually talk about this in more detail, but expectation is a sum or integral. So we're moving a derivative past a sum or integral. And it could be possibly that the sum or integral converges, but when you move the derivative in, it doesn't. We need both of those things to converge. So I know some of you know things like monotone convergence theorems and stuff. I just don't want to derail us at this point. I just want to do the statistics. So I'm going to move the derivative inside, and it's equivalent to moving the derivative through a sum or integral. So this is the expected value of d dt. Let's just assume we can do it. And we can, because things in probability are just nice and bounded. So if we take that derivative with respect to t, we bring down an x, we get x e to the tx. And so if you evaluate this at 0, so if we look at mx prime of 0, we're going to get the expected value of x, e to the 0, which is the expected value of x, which is the first moment. We have generated a moment. And if we take another derivative, we're just going to bring down another x. So if you look at the second derivative of the moment generating function, that's going to be the derivative of our first derivative, which was the expected value of x e to the tx. And so if you bring that derivative inside, x is just a constant, so you end up taking the derivative of e to the tx with respect to x, which brings down another x. And if you evaluate that at t equals 0, then you get the expected value of x squared, or the second moment. And it's pretty easy, I think, to see what's going to happen if you take a third derivative. You're going to get an x squared there and an e to the tx. And when you plug in t equals 0, the e part will go away and you'll get the third moment. Normally at this point, I would do an example like I would take our Poisson moment generating function and take a derivative and plug in t equals 0 and say, hey, look, we got lambda, and that's the expected value of x in our column. But that's just kind of busy work. I don't think we need to do that unless you really insist. By the way, moment generating functions, for them to be useful, they have to exist for t. So the domain has to include 0, because we do care about plugging in 0. So if you compute a moment generating function and it only exists for t less than some negative number, then we can't get these moments. So you'll often see in moment generating function stuff, when people write stuff down, they'll say, this exists for all t in some neighborhood of 0, because that's the interesting part. Okay, but what's really interesting, at least to me, is part C, and that is that moment generating functions uniquely determine distributions. This is an awesome property. If you have two random variables x and y, it is possible for this isn't going to make sense in terms of notes, so I don't know if you want to write this down. I'm just going to scribble something and then erase it. But you might have two random variables x and y, and they could have the same mean, right? That doesn't mean they're the same distribution. We haven't talked about the normal distribution yet, but that's defined in terms of a mean and variance. So maybe x has the normal distribution with mean lambda, and y is a Poisson random variable with parameter lambda. They would both have the same mean. That doesn't mean they have the same distribution. And if they both have the same second moment, that also doesn't mean they have the same distribution. And in fact, they could have infinite matching moments. And I put an example in the notes due to, I don't know how you say his name, C.C. Hyde. There's an example in my notes of a distribution with infinite matching moments, with two random variables with infinite matching moments, but that still doesn't mean that the distributions are the same. But if their moment generating functions match, it does. So if a moment generating function for x is equal to a moment generating function for y, then x and y have the same distribution. And we would write this just in general if we're trying to talk about two random variables having the same distribution. We would say x equals y, but put usually it's lowercase d over the equal sign to say they're equal in distribution. That doesn't mean they're equal, but they follow the same distribution, which is, we've already seen lots of things like this. Our IID random variables are all equal in distribution. So to prove this, it's a little bit beyond the scope of this course because it involves Laplace transforms. And I don't think everyone knows about Laplace transforms, and the kind of courses you need for that is not a prereq here. But it's a Laplace, just for the record, for those of you that know, it's a Laplace transform inversion thing to prove this. And so let me write this out. If you had two moment generating functions that were equal, and let me say they were continuous, just so that I can write integrals, but they could be discrete. So if we have the integral from minus infinity to infinity of e to the tx times the PDF for x dx, if this is equal to the integral from minus infinity to infinity of e to the ty, okay, x and y here are dummy variables. What's really important about this is I'm going to use the PDF for y. You know, the PDFs are different. Then if you've seen Laplace transforms, these almost look like Laplace transforms of the PDFs. If you haven't, that's fine. And you can, in theory, although maybe not in practice, invert a Laplace transform. And so my claim is that if these are equal, then you can come up with like a formula for going to be an infinite sum kind of thing, power series expression for fx, and you can come up with the formula for fy, and they're going to be the same. So I guess I need to put an x in this one. You know, two different functions. So I could have gone through this integral with like an x here and an x here and an x here. But the subscript on the f's are different. Yeah, the same everything. So the name and the parameter, the name and the parameters, so everything identical. This is so powerful. And this is really useful for finding distributions of what I call big fat sums. We've looked at some like x1 plus x2, and we've done things like that. We could find a distribution for an x1 plus an x2 using the Jacobian method, and we would define y1 to be that sum and y2 to be something else, and then get the joint PDF for the y's and then integrate out the y2. But suppose you want to find the distribution of a big fat sum x1 plus x2 out through xn. I'm writing this as an example, but this is like sort of way more than an example. This is one of the main reasons that you're going to have, I think, to use moment generating functions. Suppose that x1, x2, etc. are independent and identically distributed from some distribution. And so the moment generating function for each one is going to be the same, right? Because if you find the moment generating function for x1, that means you integrate or sum e to the tx times the PDF for one of the x's, right? And they all have the same PDF, so they all have the same moment generating function. So let's find the distribution of a random variable y that comes from x1 plus x2 plus out through xn. If that x1 in my subscript or the moment generating function is confusing, you might just call it the moment generating function for x. It's just a typical x in this list and not even use the subscript, but I can certainly call this x sub 5. They're all the same. Okay, so the moment generating function for y is the expected value of e to the ty this is the expected value of e to the t times the sum as I goes from 1 to n of the xi. This is e to a product. So that symbol is like the big sigma notation for a sum. That's a product of e to the t xi. And then because they're independent, that's part of the IID, you can pull the product out. So this is just a generalization of me saying much earlier that if x and y are independent, you can break up an expectation of a product like this. So I'm just doing that with a whole bunch of things. E to the txi. And so each one of those is the same moment generating function, because to compute this, you would put e to the tx in front of the PDF for xi, but they all have the exact same xi. So this is just, I don't know if I should write this, but it might look extra confusing. The expected value of e to the tx1, this is by identicalness. And that's the moment generating function for one of them. And you've got it over and over again n times. So we've got the moment generating function for x1 of t raised to the nth power. If I didn't make these IID but just independent, then I would have stopped here and written this as the product as I goes from 1 to n of the moment generating function for xi. If they were not identically distributed and had different moment generating functions, I can still express the moment generating function of the sum in terms of the individual moment generating functions. But it gets even simpler if they all have the same moment generating function. So here's why we care. Does that make sense? I want to get back to uniquely determines the distribution. Okay, so for example, if you compute the 240, not 250, my sticky note. If you compute the moment generating function for the exponential distribution, let me just do that one really quick. So if x is exponential with rate lambda, then the moment generating function for x is the expected value of e to the tx. And this is the integral in general minus infinity to infinity e to the t little x times the PDF for the x's. And this is the integral from 0 to infinity of e to the tx. And then the PDF is lambda e to the minus lambda x dx. And I would combine the e's and write this as the integral from 0 to infinity of lambda e to the minus lambda minus t of x dx. And that's starting to look like a new exponential with parameter lambda minus t. But the parameter for the exponential has to be greater than 0. Equivalently, if you weren't thinking about PDFs, if this lambda minus t were less than 0, then this negative lambda minus t is going to be greater than 0, and this whole thing is going to blow up. So this is kind of like an exponential with rate lambda minus t, and we need lambda minus t greater than 0 either way, if we're doing integrating without integrating by thinking of it as an exponential, or if you're just doing this integral and not even thinking about PDFs. So I'm going to pull out the lambda. I'm going to put a lambda minus t in front. So I'm going to put a lambda minus t out in front of this integral, 0 to infinity, lambda minus t, not fitting, e to the minus lambda minus t x dx. And now I do have an exponential PDF integrated over its whole support. That integral is 1. So integral is 1. So we get lambda over lambda minus t. And it only holds for t less than lambda. So if you went to your table and looked at the exponential row, you would find this moment generating function over in the moment generating function column, and you would see the restriction t less than lambda. Okay, back to the example. I guess that's just another example of a moment generating function. So let me get to the actual thing I wanted to show you. So suppose x1, x2, xn are IID exponential with rate lambda. I want to find the distribution of the sum. Now, if this were to appear on the homework or something, I would say, okay, big fat sum, I want to use moment generating functions. And then you don't have to find the moment generating functions unless that's the specific point of the problem. The homework problem says derive the moment generating function for this. You know, that means compute one. But otherwise, if you're just using it as a step in finding a distribution, feel free to grab them off the table. Okay, so we know that the moment generating function for y, because they're IID, this is the moment generating function for one of the x's, that's a t, raised to the nth power. And the moment generating function for one of them, for the exponential, is lambda over lambda minus t raised to the nth power, and this holds for t less than lambda. So now I realize we don't know a lot of moment generating functions, but I meant to have the table ready to go. It'll just take kind of a long time for me to share that and find it. If you go to your table of distributions and you think, okay, the exponential is a continuous random variable, so the sum is still continuous. So if you go to the continuous side and look at all the moment generating functions and look for something like this, this is very much like what appears in the table to be beta over beta minus t to the alpha, which is the moment generating function for the gamma distribution with parameters alpha and beta. From this, I can specifically say this is the moment generating function for the gamma distribution with parameters n and lambda. So alpha is n and beta is lambda. And so we can conclude, because moment generating functions uniquely determine the distribution, that the sum of exponentials has a gamma distribution with parameters n and lambda. And that is by uniqueness. So if the moment generating function is that of the gamma, then the random variable must be a gamma. This is why I think they're super powerful. There's some other transformations that might be easily figured out, the distributions of the transformations using moment generating functions, but mostly big fat sums. And if you look down the moment generating functions in the table, your eye is going to be drawn to some things that look like other moment generating functions raised to a power. So you can kind of look through the table and figure out a lot of things that are sums of other random variables. For example, if you have your table in front of you, the moment generating function for one of the negative binomial distributions looks like the moment generating function for the geometric distribution raised to a power. And the geometric distribution is supposed to be the number of successes until the first trial of something, where you've got success and failure with probability P of success and independence. And the negative binomial, one interpretation, is the number of trials until the rth success. So you already saw in homework 1 that that negative binomial with r equals 1 is just the first success, brings you back to the geometric. But now we know that the sum of geometrics is a negative binomial just by looking at those moment generating functions. And that kind of makes a lot of sense, because if you want to go until you see the rth success, you can just go until you see one success, count that many trials, and then go until you see one success again, count that many, and then go until you see one success again. You have to add up, for our successes, our different geometrics. So if you don't have the table right now, check it out. Check out the relationship between the gamma and negative binomial moment generating functions, and maybe look around and see if you can easily find other distributions where you know the distribution of the sum of n of them. that is a proper sentence. So this is just another arrow on that table that I posted, adapted from Lemus with all the distributions and the arrows between them. So for us, the first, and we need this so much. So for us, whenever we sum up exponentials, we get a gamma. And the first parameter is the number of things we added together, and the second parameter matches the parameter for the gamma. It is possible that someone uses the different notation for the gamma and not the exponential, or the other way around. So you might possibly see this written as gamma n 1 over lambda somewhere. It depends on how they parameterize their gamma distribution or their exponential. I'm going to really blast through one more moment generating function. So let's find the moment. No, actually, sorry about that. It's a new distribution. I'm sure most of you have seen this, but I'm about to introduce the normal distribution. So we say that X has a normal distribution with mean mu and variance sigma squared, which variance has to be greater than or equal to 0. Equal would be a really degenerate random variable that if the variance is 0, then you don't have a normal distribution anymore. You've got a random variable X that equals mu with probability 1. There's like no spread around it. If X has PDF, f of X is 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared x minus mu squared. And then there's generally no indicator on this because it holds for all x between minus infinity and infinity. So you can certainly write an indicator from minus infinity to infinity, but I think we talked about this before. That would be like running around and multiplying every function you ever wrote down by 1. It's just not necessary. And this distribution is the bell curve. It's supposed to look symmetric, although I'm not going to, no, it's not that bad. So it's centered at mu, and if you did some calculus, it would be easy to show that a distance of 1 sigma, so the square root of the variance. So if you take sigma defined to be the square root of sigma squared, this is known as the standard deviation of the distribution. For any distribution, the square root of the variance is known as standard deviation. And usually you want to talk about standard deviation when you want to get back into the units of the problem. So if you're measuring lengths of fish or something and you return a variance, it sort of comes out in squared units. And if you want to get back into the units of the problem, you might look at the square root. But going back to the graph, this point where it changes concavity is 1 standard deviation away from the mean. That's exactly where it goes from like concave down to concave up, or concave to convex, or whatever you want to call it. So easy to see once you know that large variance means you get a really spread out, flat, mushed down curve. And small variance means you get something really spiky, but still a bell curve. Okay, so we write x squiggly line n mu sigma squared. Occasionally, but these people are in the minority, they'll write n mu sigma. Most people put the variance there. So the point is that I wanted to do a moment generating function example. Suppose that x is normally distributed with mean mu and variance sigma squared. Let's find the moment generating function for x. This one's a little tricky. So I guess before that, I want to say using the G inverse transformation stuff, we can show that if you have x normally distributed with mean mu and variance sigma squared, and you subtract its mean and divide by its standard deviation, you get a normal with mean 0 and variance 1. And the other way around, if you have, so usually normal 0, 1s are known as, they get the name Z in statistics. It's not that unique of a name that I can guarantee you that every Z you see is going to refer to this so-called standard normal. But we can go the other way. So if you have Z, a normal random variable with mean 0 and variance 1, we can build up a random variable with mean mu and variance sigma squared like this. So the fact that we maintain normality, that you would have to show using a G inverse or possibly using a moment generating function. But we can't do that until we know the moment generating function, and that's what I want to compute here. And the fact that the mean becomes 0 and 1 when you make this transformation, and the mean becomes mu and sigma squared when you make this transformation, should not be surprising, right? Because you can compute, for example, the variance of, like if you have x normal mu sigma squared, then the variance of x minus mu over sigma, you can pull out that constant 1 over sigma, but it comes out squared. And we talked about variance. If you add or subtract a constant, it doesn't change the spread. And the variance of x in this case is sigma squared. So that's 1. So it might be surprising to you that these simple transformations maintain the normal distribution, but the fact that the means and variances changed as they did is really easy to show without any transformation. Okay, so to the example, I'll leave that there. We're still writing that. So suppose that x is normal 0, 1. Yeah, we can call it z, but we don't have to. Let's find the moment generating function for this distribution. And then I'm going to use that to get the moment generating function for a more generic normal distribution. So the moment generating function for x is the expected value of e to the tx. This continuous distribution, we're going to integrate e to the tx times the PDF. This is the integral. It does stay minus infinity to infinity because that's the support for this distribution. And the normal 0, 1 has the PDF 1 over the square root of 2 pi e to the minus 1/2 x squared. I just plugged in sigma squared is 1 in what I wrote down earlier. And so to do this, I'm going to combine the e's. Again, though, if a question on the homework or an exam says, show this distribution is equal to this, or find the distribution of a sum, you don't have to derive the moment generating functions. Just if you're specifically asked, derive the moment generating function. So I'm going to combine these e's, and because I want to kind of use integrating without integrating and get another normal back, I'm going to leave a negative 1/2 out front, and I'm going to write this as x squared minus 2tx. And then to make it really look like a normal, I'm going to complete the square of that exponent. I could remind you about completing the square, the method. We're not going to need it very much. So here, in the interest of time, I'm just going to guess. So I want to write this as x minus something squared. And I can write it as x minus t squared, which will give me x squared minus 2tx plus another t squared. So I have too much stuff in there. So I need to multiply by e to the, so taking into account the negative on the 1/2, I'm going to need a positive 1/2 t squared. Or maybe I should have written that first up in the exponent. You can just leave it. You don't have to change this, but I'm going to write it this way. really, when completing the square, you look at, let's not talk about that right now. That's a pretty easy kind of guess though, in this case. Okay, so if you factor that e, you've got an e to the 1/2 t squared, and then the rest of it, is the integral of a normal distribution. If you go and look at the PDF we wrote down today, it looks like a normal distribution with variance 1 and mean t. So this is the PDF for the normal t1. And so it integrates to 1, and we get e to the 1/2 t squared. Okay, so the last thing I can fit in here is that's the moment generating function for the normal 0, 1. So this other example here, so now I'm going to let x be normal mu sigma squared, and I want to find the moment generating function. So we can let z be a normal 0, 1, and we can say that x has the same distribution as sigma z plus mu, based on something we haven't shown, but we can do the G inverse stuff. And I think I have a minute. So the moment generating function for x is the expected value of e to the tx, and this is the expected value of e to the t times sigma z plus mu. And if you multiply that stuff out and pull out the constant, you get e to the t mu, expected value of e to the t sigma z. And that part is going to be the moment generating function for a standard normal with t sigma plugged in for t. And we just computed the moment generating function up here for a standard normal. So this is e to the t mu, e to the 1/2, and in place of the t squared up here, I'm going to put the t sigma. And so this all comes together as e to the mu t plus 1/2 sigma squared t squared, which is what you'll see in the table for the more general normal distribution with mean mu and variance sigma squared. Okay, so I am out of time, but next time we start the course. So first we did prereq stuff. That was chapter 0. And then we did these 4 tools, which is not prereq stuff. You're not supposed to know this coming in. Come back. Thank you.